So here we look at the time domain analysis of any given system, right? So in case of a control system, right, we have, say this is the h of s, input is r, let's say the output is c of s, right? Control systems are to be designed in such a way that for a given input it should be producing an output, right? In addition to this, there could be what is called as a uh, disturbance signal. Okay, so I'll call this is say g of s, right? So there could be this is what is called as the disturbance signal. So whenever we uh, consider the system's input, right, it produces an output c of s, but there are some things which we don't have any control. Okay, it's a disturbance could be internal or the external, right? So whenever the disturbance affects the system should be designed in such a way that it automatically takes care of the disturbance and how to nullify the disturbance, the effect of the this g of s on the output c of s, that needs to be studied. For that reason, what we do, we try to define the disturbance in terms of some standard signals, right? So the standard signals to model the disturbance. Standard signals to model the disturbance. We know that we are using three different signals. The first one is the step signal. Okay, this is nothing but u of t, standard definition. So we, since it is represented using Laplace, what is Laplace of u of t? Do you remember? Laplace transform of unit step function. Sure. One minute. Okay, so this is right. That's correct. So first function is this. We try to model any type of disturbance, right? Using some of the standard signals, but one of such standard signal is unit step. Then we go for a ramp signal, that is r of t. So what's the Laplace of r of t. Okay, so this becomes 1 by s squared, and then we use the third signal. This is the parabolic, right? This is denote no standard notation. It's t squared by 2. Can you tell me the Laplace of t squared by 2? Yes. Or even if you tell for t square, it is fine. We can anyway divide by 2. Hmm. Yeah, that's right. We have a standard equation. Yes, sure. Okay, okay. That's fine. Yes, sure. Yeah. Yes. So it's no, it's n factorial. This is the formula. If you remember, if you have a t to the n, this can be proved. T to the n is n factorial by s to the n plus 1. Okay, so t square becomes 2 factorial, which is 2 divided by, right, 2 into s to the power 3. So this cancels, so your answer should be 1 by s cube. So just to cancel the 2, we have a 2 in the denominator on the left hand side. This is called as unit parabola. All right, so these are the three signals which we are going to use to represent any disturbance or unknown signal that arises inside the considered system, or it's an external case. Now, let us consider under what conditions a system becomes stable or unstable, right? Because of the inputs, right? So we try to model in order to analyze the system's performance under disturbance, right? What we try to do, we try to generate the um, such signals. We will generate such signals and we provide them as inputs. Okay, just to analyze, right? So this is the disturbance analysis, right? So how do you do that? You can, this is the same system which is under consideration. Now the input itself, it will be a known disturbance. Disturbance is given an input to calculate an output, right? So our intention is to look at the performance of the system under various disturbance signals, right? Normally the disturbance signals are completely unknown. Okay, right? We cannot predict what exactly is going to come up as a disturbance signal. Okay, but there are some situations wherein you can guess what's going to happen, though you cannot specify or you cannot exactly identify the value before it comes. Okay, it's something like a load of maybe electricity. Electricity load is one example, which is actually a disturbance. Okay, and we know that maybe for a power supply station for a city, right? The load consumption at a given point of time, right, is a disturbance, right? So you see that exact value is unknown, right? But we know that our city consumes highest load maybe at 7 p.m., right? Every day, right? This can be guessed because everybody will turn on their home appliances and everybody will be back home at that time, right? It's going to reduce as the time progresses from 7 up onwards, right? So maybe 9 o'clock, 10 o'clock, 11 o'clock, load reduces. Okay, but exactly by what amount, what will be the exact value of the load, right, of the whole city today, right? We cannot guess, but this shape can be guessed. Okay, it's maximum, then it reduces, right? You can come to a close approximation by looking at yesterday, day before yesterday's data, right? But not exact one. So you see that that disturbance signal is what is considered as you can guess the shape. But when it comes to the communication or any other this thing, the noise is a disturbance over there, but you cannot predict, right? Because of the uncontrolled behavior of the channel, right, where you are communicating. Okay, so now that's why the disturbance analysis is very important. It's going to affect the performance of the system, right? Okay, now this is our model. Now what you do, you we understand that we have to give the disturbance itself as an input, right, to understand, right, the characteristic or how the system is going to behave when there is an uncontrolled input or unknown input, which is a disturbance. So what we do now, let's try to define some of the terms here corresponding to a given system, right? So let us say that there is a system, the H. or h of s. Let's say that we give the h of s as maybe let me just assume that okay, this is 1 over s plus 2 into s plus 5. Okay, let me say this is the system. Okay, now let me say I am going to give an input, right? That is a C of okay. Let me give the input. Let the R of S be equal to 1 by S. Means what? I'm giving input as it's 1 by S. So what is the time domain signal is? What's the input? Input is which signal? It's U of t, correct? I'm giving U of t as input, right? So U of t, one of our standard signals. You can give it to model the uh, noise or the disturbance. Okay, now if this is the input, then what's the output? How do you calculate the output? So I'll write therefore output, say C of S is equal to, it's actually the product of R input and H, which is the transfer function, correct? So this is a transfer function, that is H of S into R of S. So let's multiply. So this the system's function is 1 divided by, this is s plus 2 into s plus 5 into this term, it is 1 by s. Now this is equal to uh, anyway, I'll write the simplified one. This is s into s plus 2 into s plus 5. Now we have some terms coming up. That is, let me take the output now. So this is the actual equation. Whatever we are writing here is corresponding to the output, correct? That is C of S. So the Laplace transform of my output, how can we calculate? This has to be which technique you are applying to get the C of t now. Let me assume I want a C of t. Yes, okay, let's do that. So C of S is equal to, this is, I'll say A by S plus B by S plus 2 plus C by S plus 5. Okay, uh, fine. Then let's calculate the values of A, B, and C. Okay, yes. Yeah, yes. Yes, yes, yes. You have to eliminate the denominator of A from the main equation, and then we will, yeah, so this is the equation to calculate A. A is equal to, write the same thing without this S. Okay, so that means it should be 1 divided by 0, because when you are taking out the S, means S is not there, put that S equal to 0. Okay, so this means you are writing S plus 2 into S plus 5 with S is equal to 0. 1 by 7, right? 1 by S into S plus 5 with S being equal to minus 2. 1 by 6. Okay. Yeah, minus 1 by 15, right? Minus 5 minus, yeah, plus, right? 1 by 15, isn't it? Okay, so we got these values. Let's write them down. Therefore, the C of S becomes equal to, this is 1 by 7 over S. Then we have minus 1 by 6 over S plus 2. Then this is plus 1 by 15 over S plus 5. Now, right? So we can see that, all right. So from the, yeah, yeah, please tell me. Yeah, 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 we can come back to C of t. Okay, let's write the C of t first, then I'll define some terms which are important throughout the control system concepts. Okay, so what is this? This is simply 1 by 7 into u of t, correct? So this is minus 1 by 6 times minus 2t into u of t. This is plus 1 by 15 times e to the minus 5t into u of t. Okay, that's right. So we got this. Now, uh, fine. Okay, let's try to define some terms now. Let's go back to the given transfer function, right? So the transfer function, I can see that it is of order 2. Its a denominator has the highest power 2, s square. So it's a second order system, right? And because of that, we have two roots of this denominator, right? So the roots of denominator are called as the poles, right? So we can see that there are two poles of the system, right? The two poles given in the system will come in the output as it is, right? So corresponding to the system, you have two poles, so they are called as the system poles. All right, then let's go back. Let's check out the input, right? Input is 1 by s, right? So do you have a pole or zero over here? Again, you can see that there is a pole, correct? There is a pole at s equal to 0, at pole at origin, and this pole is because of the input, correct? So again, I can see that in my final output there is a contribution of this pole to my final output, right? So that pole is called as the excitation, because it's an excitation to the system you are giving as input, right? Yeah. So that's why it is called as excitation. Excitation pole. Assume that you had given an input like 1 by s into s plus 1, maybe possible, right? Again, you will see that the s and s plus 1 over here as two different terms. Okay, as of now you gave only one input, right? One pole was given as input, it's present in the output. Okay, these are the first two terms I wanted to define. Then there is another, okay, there are two more terminologies to be defined. Okay, now okay, so from the C of t, I'll try to define the two more terms now. So let's put this limit t tending to infinity C of t. Let's try to calculate that. In the sense, it's like something like you are trying to calculate the final value of your output. Okay, C of t has an equation which we just have calculated, right? And I want to find its final value. So final value, you can apply even even this thing can be calculated from the Laplace final value theorem we had, right? Doesn't matter even if you don't remember, we can calculate the same thing using c of t. Put t equal to infinity in the equation c of t, that's all. Okay, limit t tending to infinity, put a very big value to t over there, and write what value you get. Yeah, you will put infinity preferably. Okay, so you see this first part is 1 by 7, u of t will not change even at t equal to infinity, correct? So this is 1 only, correct? Minus 1 by 6 into this is e to the power minus 2 into infinity is infinity, right? Into u of t, that is 1, right? Plus same thing 1 by 15 into e to the minus infinity into 1. What is this term? E to the minus infinity. What's this value? It's a 0. So both the second and the third term of the above equation reduces to 0. So you see this is 1 by 7. In the sense, the output tends to become 1 by 7, right? When time goes to infinity, right? So we have few more terms to be defined now based on this. So that is, see, this is something and these two are is something else. Okay, so the one, those terms which are because of the system's poles, right? So system pole is defined in Laplace, right? In term, whenever you are in S domain, you call them as poles. Okay, when it comes to the time domain, it is a response, right? So this response, whatever equation we wrote here, this is the second and the third term, the e to the minus 2t u of t and e to the minus 5t u of t, those terms will vanish when time is equal to infinity. So they are called as the transient. This is transient response. Okay, and the 1 by 7 into u of t, which is because of the input, correct? The input given is 1 by s, because of that whatever output you get, right, in the c of t, that remains there even after time is equal to, it was there at the it was there initially, it will remain even when time equal to infinity, correct? So this is called as the steady state response. So two terms are important. One is a transient, one is a steady state. Steady state is the one which remains in your signals, sorry, system's response even after time t becomes equal to infinity. That's why steady state. All right. So there is another term called transient which will vanish as the time progresses. Okay. So just to look at this in using a graphical representation, right? Let me say, let's assume, right? So let's say that this is the time axis, this is the input as well as the output. I'll try to plot for the same. Okay, input or the output. Let me assume the input as discussed, it's a 1 by t. So let's say this is the input, right? This is 1. So given at t equal to 0, this is the input. Okay, for output, let me change the color so that, okay, so this is the output. Now output, see, you see output is actually going to be say 1 by 7, maybe I assume this is 1 by 7. Okay, so 1 by 7 is expected to be this value. but this value will be reached only at t equal to infinity, correct? Before that it's a smaller value because you are subtracting something from there initially, so it will be like this. So you see that 1 by 7 will be reached at t equal to infinity. So this is the transient which you can see, right? It actually has a bigger value now, right? That value keeps on reducing so that you reach the 1 by 7, right? So that's the meaning. All right, so we understood that the because of the poles present in a system, right? It can be the pole because of the input or the system poles, maybe excitation pole or the system pole. What we understand is that the system's stability can be identified. System, what system's response when t equal to 0, when t equal to any specific time, or even when t is equal to infinity, can be found using this. Okay, so that's the first thing to study. All right, now after this, now we'll go for the types of system. Okay, so basically we have in practice we use two types of systems. Okay, so the first one is depending on what is the power of s in the denominator. So right, we classify them as two types of system, two different orders of system. The first one is first order. So first order system, right, generally denoted as g of s is equal to some value. Maybe you can write this as k divided by this is s plus tau. Okay, now we can this is here the k is called as the gain of the system. Okay, and the tau is referred as the time constant of the system. Now, quickly, let's not solve any problem over here, but just to understand why this is called as the uh, system's time constant, right? We can just try to understand the by calculating an output. Okay, so let the input be u of t, right? That means the Laplace will be 1 by s. So calculate the system's response. C of s is equal to g of s into r of s, that is k divided by s into s plus tau. Okay, so this means normally we get two terms at the output, right? So that could be something like a by s plus, maybe I'll just assume b by s plus tau. Write the equation c of t. This is equal to a into u of t plus b into e to the minus tau times t, correct? Tau times t into u of t. So you can see that there is a time constant. This minus tau is the rate at which your transient will reduce, right? So this is the transient. The first term a into u of t is the steady state, correct, as per the definitions we just discussed. So the tau controls the decaying of the transient, right? Hence called the time constant. Are you okay with this? Now, you see that with respect to this, we have certain, what you call, the terminology is coming up. One is tau, which is the equation, or which represent the decaying, and k is the gain of the system. All right. Those are the two terms to be defined. Then we'll go to the second order system. Right. So in general, the second order systems equation we always try to represent in the following format. Okay. Okay. The we will write the transfer function. Say the g of s looks like omega n squared divided by s squared plus 2 times zeta omega n into s plus omega n square. This is the format because the denominator has highest power s square. Okay, this is the standard equation. Now, depending upon right the values of zeta and omega n, the response of the second order system will vary. Okay, so let's define the terms now. Here, omega n is called as the undamped natural frequency, right? So then this zeta is defined as the damping ratio or damping factor, right? Now, if at all we want to represent this particular function using the, if at all you want to write the second order system using a feedback, right? Then what we are supposed to write, we'll see. Okay. For that, I'll make a slight modification. It's not. I'll change the notation because G of s and H of s are used to represent the forward path and the reverse, the feedback path. Okay. So if I simply write G of s, it makes sense that it's only the forward path, no feedback. Okay. Just to make a change here, I'll write this as the output by input, C of s by R of s. This is the output. Okay, actually this is the transfer function, but if at all I want to write this as a feedback, okay, so this is the feedback block diagram of a second order system. It's used many times. Okay, so we have R of s coming here. Let's take this as a negative feedback. This is plus, whatever comes from the bottom will be negative. Now we see the G of s is equal to omega n square divided by s into s plus 2 times zeta omega n. So this will be the forward block. This generates an output that is C of s. This is C of s. Now take this and give it as input with a unity feedback. Okay, so this is the h of s equals to 1. Okay, so now what is the C of s by h of s for this system? How do you C of s by R of s? My mistake, not h. What's the equation? General equation. Consider this to be in terms of g and h, right? If you want to write that, the equation should be g of s whole divided by 1 plus g of s into h of s. Correct? So can you put the values here now? Put g of s is equal to this, h of s equal to 1 over here. Okay, so this g of s comes here, the h of s is substituted here, and simplify and check what you get after simplification. Okay. No, I think that one should get multiplied with the s into s plus 2 zeta omega n, right? When you make the common denominator in the denominator. So when you substitute, what happens? Just substitute first. So let's substitute now. This is equal to, the numerator is omega n square by, this is s into s plus 2 zeta omega n, isn't it? Whole divided by, you say this is 1 plus the same thing, right? Omega n square by s into s plus 2 zeta omega n. Now as it is, I cannot cancel the denominators because, right? Right. Whole divided by, now the s into s plus 2 zeta omega n comes to this side. This is 1 plus omega n square, now whole divided by that term, correct? This and this will cancel, right? Now you can expand. So therefore this is equal to omega n square divided by s square 2 zeta omega n into s plus omega n square. So just compare this with what we already have written. This is the standard second order function. So the standard second order function can be written in the form of a feedback like this. Okay, because the negative feedback is most commonly used, right? So how to generate a second order system with the negative feedback, right? Is this is the answer. Now, so under this condition, we have various terms to be defined, right? So that is, let's say, the response of second order system to the step input. So it's like the previous case. Previously, we gave the step as a standard input, the u of t. Okay, now when u of t is given, we have different systems to write. The first case is called as the underdamped case. Okay, so this is underdamped case that is controlled by the zeta value, right? So 0 less than zeta less than 1, right? So it's like you have the same system, g of, this is the system transfer function, right? You give input as unit step and look at what is the output. Okay, so again, actually we have a derivation coming up over here. We'll skip that. Directly I'll write the output. All right, so the output c of t is equal to, this is the standard equation which is widely used. So 1 minus e to the minus, this is zeta into omega n into t whole divided by root of 1 minus zeta squared, 1 minus zeta squared into cos omega dt plus, this is zeta into sine omega d into t. Okay, so this is the equation, right, of the system, right? Now here we are defining a new term called omega d. Okay, omega n is known, zeta is known to us, right? So what is omega d? Omega d is called as damped. Omega n is undamped. Okay, this is damped natural frequency of the system. Right. Now, actually, some other textbooks might give the same equation in a different format. So that is also I'll try to give it. So this is equal to 1 minus e to the minus zeta omega nt divided by 1 root of 1 minus zeta square into, it may look like a sine function, sine of omega dt plus theta, okay, where the theta is equal to the tan inverse of 1 minus zeta square whole divided by zeta. Then we have the second case called undamped. So undamped is a case where zeta is not there. Zeta is completely zero. Okay, so this case the output, again we have a derivation, but we'll skip this. Directly we'll write the required answer. 1 minus, this is cos of omega n into t. All right, that's the next case. Then we go for a third case. This is called as a critically damped. This is zeta equals to 1. Okay, this is exactly equal to 1. Huh. All right. So in under this condition, the C of t is equal to 1 minus e to the minus omega n into t, 1 plus omega n into t. Then we have the overdamped. This with the zeta value greater than 1. So here the C of t is equal to 1 plus omega n whole divided by 2 times root of zeta square minus 1 into, this is e to the power minus, so there will be some constants coming up depending upon the roots of the equation. So if the roots of the equation are s1 and s2, I can call it as s1t by s1, okay, e to the minus s2t by s2. So here s1 comma s2, they basically represent the poles of the system poles. Out of these many what you call types of systems, the one which widely uh, gets accepted while implementation of any system is the underdamped case. Okay, it's between 0 to 1. So let's plot the one first. So the plot of c of t, right? Correct, correct, right? So we will plot the poles, exact location of poles, and then we will trace out for stability. Okay, right. So in terms of the response of the system in a time domain, right, this is the answer. Let's try to plot a graph. All right, let's say this is the input is u of t, right? Maybe this is say 1. Okay, and the output in case of the uh, underdamped condition, there is a, you can see that this is 1 minus the equation, you can see it's 1 minus something, and that has a controlled exponential decay e to the power minus zeta, correct? If you look at the equation of the underdamped answer c of t, black, see this term, this is when you put t is infinity, this is gone, correct? That means my final answer is 1, right? So before that I have a controller, right? That controller is e to the power zeta. Okay, I'll go to this function, this is more easier to understand. Okay, so my final answer is 1, and before that I have a sine function controlled by this e to the power minus zeta omega n into t. It's a sine wave, but there is a boundary controlled by e to the power minus zeta omega n. So put t equal to 0, this is highest, correct? E to the power minus zeta e to the power 0, which is 1. So my at t equal to 0, where is the signal starts from 0, because put e to the power minus zeta omega n into t 0, put 0, e to the 0, e to the 0 is what, 1, correct? So 1 minus 1 is 0, so your signal actually starts from here. This is your response. It begins from here, it goes like this, comes down, it's a sine wave. Okay, so this is the response of this, right? Okay, now we have to measure something from these graphs. Okay, the first one, let me mark this time. Okay, so this is one time. First time it is crossing that final value, which is called as the rise time, TR. Okay, first time it reaches the peak is called as TP, the peak time. Okay, from 1 it actually goes to a peak value. So above 1, how much ever it goes, right, that is called as a maximum peak overshoot, MP. And then we have what is called as a settling time. For that we need let's say, okay, we have small amount of tolerance on both sides. Okay, I think I cannot show the tolerance over here. Let me make the tolerance higher. Okay, so let me assume that this is the tolerance. On both sides I have to draw the similar tolerance line. Now, so the tolerance, why the tolerance is used, because see, it's going to take infinite time to reach 1. Okay, to reach one and you cannot wait for that long. So what you do, you define the tolerance. If it comes within this percent, maybe this is 5%. Okay, 5% tolerance, right? In the sense, above you have 1.05, below you have not minus 0.95, right? 5% tolerance. So whenever your signal enters the tolerance band and never leaves after that, for example, you see this point. See, once it enters inside this now onwards, it will not go out. Correct? See, it's well within this band. The response is well within this band, right? So such point is what is called as the settling time, right? So this is the settling time. So denoted by TS. Okay, so the when to by the system's response to enter inside the tolerance. Output is well defined within the tolerance band. Time taken for that is called as a settling time. Right? This value varies depending upon the threshold value or the tolerance value. If you keep it as 2%, you see that the values will go down. Correct? So let me say I'll change the color to a different one just to mark that. Let's say this is 2%. Okay, now you see 2% is not entered yet, right? In both the cases it's not 2%. 2% is somewhere here. It will take much more time to reach the 2% band, right? Maybe somewhere here you reach the tolerance, right? If it is for 2%, right? So this is for 5%. Maybe this is the same TS for 2%. Okay, so there is a difference depending upon what threshold you take, right? 5% or 2% or whatever. 5 and 2 are the standard values. Okay, so depending on that, you can uh, find out the TS. So correct, right? So depending upon the specific value of the tolerance, the TS will change, right? We have different equations for that. All right. So I'll give the equations in the next class, and then we'll go to the stability concepts. Okay. But we have a concept called ESS, that is a steady state error, right? So we'll finish that, and then we'll quickly go to the stability concepts.